what was your favorite math course that you took?
In undergraduate or ever?
Undergraduate.
Undergraduate. Okay.
Big one.
I would have to go with. I think I would. I think I would go with like an introductory topology course.
Topology course.
Yeah, topology, because that's a very new concept, and like abstract algebra. It's abstract algebra, but topology is something that like you don't see, or you don't know that you're seeing. You're seeing it very early on. You just don't call it topology. Like, for example, I can give an example. So a set, I've mentioned this on my channel before, but like a set, okay, a set does not have a shape to it. A set's just a bag of crap. So like the real numbers is a set. When you draw it as a number line, that's the topology of the real numbers. That's additional information. The shape of it is the topology to some degree. It's a little looser than that, but sets don't have a shape. So whenever you tell a calculus student to draw the real R2, or the Cartesian product of the real numbers, the plane, the fact that it's a plane, that picture is coming from the topology of the set. It doesn't come from the set. That's just so these concepts are really always there, but taking that to a new level, and it's really a new topic, more so than the others, at least among the classes that I took.
So what were kind of some of the groundbreaking like topics that you learned in that introductory course?
Okay, well, so this might be a little awkward to describe, but so when you have mathematical structures of different kinds, there are functions between them that preserve their properties. Okay, well, for in linear algebra, if you have two vector spaces, a linear transformation is the kind of function we're interested in. Well, in topology, the kind of function you're interested in is continuous functions. And what's so cool about that is that that's not a new kind of function. That's a kind of function that you've always been studying, like in calculus and all that. So the fact that topological spaces were the spaces that we were always kind of interested in for a lot of the math we've been doing is really shown by the fact that continuous functions are what preserves topological properties, if that makes sense. Because continuous functions, I mean, that's everywhere. When you take a derivative of a function that's continuous or differentiable, it's continuous. These are common concepts, and topological spaces are what those functions are always mapping between.
When I think of topology, I always think of a torus for some reason.
Every single time. I knew it.
Yeah,
I knew it.
That's a topological space.
Yeah, 'cause it's the classic. It's that classic thing, right? It's the classic shape.
Yeah. So why a torus?
I think it's like the coffee mug thing, but that's a little bit overplayed.
Maybe,
I do understand that. I remember watching like the Vsauce video where he does talk about like where you continuously like reshape it.
Like how many holes does a human have? Something like that is the name of the video.
He tricked a bunch of people into learning topology. I don't think these headphones were designed for my head shape. But anyway, so no, a torus is interesting. So this is what I like to say about the torus. So think about a two-dimensional video game like Pac-Man, where the map warps you to the other side. So if you go all the way to one side, you end up on the other side, and if you go up, you end up on the bottom, right? Well, that's a torus. Topologically, that's a torus. Think about it. You're looping through the top, and you're looping around the side. So you can think, oh, it's a circle this way, and then it loops that way. So you could think of games like Pac-Man as taking place on the surface of a torus. The topology doesn't care about the shape of it. It cares about the fact that, when you go to this end, you end up back over here. You go up, you end up over here. A game like, like Asteroids, or like, some game where you're in a spaceship and you can go to the side and up here, there, and then you're going up all the time. That might be like a cylinder or whatever. But yeah, these are all examples of topological spaces. The fact that you warp to the other side on the game map is what determines the topology, not that it's on a 2D screen. Yeah, if that makes sense.
And I remember learning about, like, just on my own, not in school, about like the way you can represent topological spaces with like the square with the arrows, where you like match up the sides and all that stuff.
Yeah, exactly.
I also, maybe if you can give like a little clarification. but I remember learning about the Klein bottle and how I believe it's a 2 manifold embedded in 4D space.
That's right.
Okay.
Well, so it can be embedded in 4D space.
Okay.
That's not like an intrinsic thing about the Klein bottle. You know
Maybe
you
want to explain the Klein bottle to those who haven't heard it before.
Yeah, so the Klein bottle is a 2-dimensional manifold, and what that means is that if you go to any place on it, it looks like a plane, okay? So like any surface is a 2-manifold, because if you look at a little spot on it, it looks like a plane, okay? Now, what's interesting about the Klein bottle is that it's non-orientable like the Mobius band, and it's also closed. Now, so let me make sure I say this in a good way. Whenever a topological space is closed, that sort of means that it doesn't have an edge or a border, but at the same time, it doesn't continue on forever. I'm trying to roughly describe this. So think of a plane. That would not be closed because it goes on forever. But if you think of a sphere, that would be a closed 2-dimensional manifold because it doesn't have a border or an edge, and at the same time, it doesn't go on forever. Okay? And then there are non-orientable manifolds like the Mobius band. Now, the point is that either of those two conditions, being non-orientable or closed, means that you need one more dimension to embed in Euclidean space. So, what that means is that the Mobius band, can you put a Mobius band in 2 dimensions? So it is a 2-manifold, but can you put it in 2 dimensions?
No.
You can't, exactly. You need 3 dimensions. Well, the Klein bottle is non-orientable and closed, so we need 2 more dimensions. So both the Klein bottle and the Mobius band are 2 manifolds, 2-dimensional manifolds, but the Klein bottle needs 2 more dimensions for Euclidean space to have an embedding.